Okay, the last video ran a little bit too long, so this is the hideously complicated question, or probably the worst one I've seen in the NCA papers in recent years. You'll see why it's tricky in a tick. This is the last part of a question, and initially Jane's dad was closer to the pivot and the seesaw was balanced horizontally. It's now balanced, but it's balanced with two support forces basically, and this is why this one's unusual. It's a bit of a wonky system. So it is balanced because it's not turning. So the clockwise torques equal the anti-clockwise torques, and it's not sinking or floating. So the upward forces equal the downward forces. In this particular case, because Jane's dad has moved to the end of the seesaw, the end of that, or the seesaw end where he is sat, is touching the ground. So the ground is providing a support force as well as the middle of the seesaw, as well as the pivot, the triangle there. So this is quite a complicated question, and I'll go through it bit by bit. I recommend you pause the video now just to read that little bit of stuff that I've put underneath the question, just to give you an idea of what we've got to try and do as we go through the question. The main issue is, by all accounts, we know Jane's force downward, and we know Jane's dad's force downward, and we know the force of the seesaw downward. However, that's all the downward forces. At equilibrium, upward force equals downward force, and we don't know the support force provided by the pivot. We don't know the support force provided by the seesaw. There is a way around that. We will use this as the pivot point, and therefore we can negate any torques created by it, and we also take out the effect of Jane's dad in the equation. I'll show you what I mean as we go through. So we start off this bit by working out the torque created by Jane. So her force is 30 times 9.8 multiplied by the 3 meters that she is from the end of the seesaw that is touching the ground. So we're working around the support force of the ground as the pivot. We're going to add to that the mass of the seesaw times 9.8, multiply that by 1.5 because that's half the overall length of the seesaw, and half of it is going to be supported by that pivot point. The other half is going to be supported by that pivot point. That is balanced out. So those are the downward forces. They are balanced out by the support force of the fulcrum there, multiplied by the 1.5 meters that it is from that ground support force there, and that's our equation that we begin with. In this instance, like I say, Fs is the support force at the pivot, and as you can see, we've got a fairly long equation there, but there is only one bit missing. The only bit that's missing is Fs. The other thing to note is that because Jane's dad is sat at the pivot point, he doesn't create a torque, so we don't multiply his mass by anything. So when we start to calculate through those brackets, we end up with 882 for the torque created by Jane. Add to another 882 for the torque created by the seesaw, which gives us, which is equal to, the support force multiplied by 1.5. What this means is that Fs is 1,764 divided by 1.5 rather, and that gives us 1,176 newtons. So we've now worked out the upward support force at the pivot point there. It's 1,176 newtons. Now, as I said at the start, the total force upwards equals the total force downwards. So what we've got to do now is to put that into some numbers. So the total force down is F Jane plus F dad plus F seesaw. We do include Jane's dad now because he is providing a downward force. He's not providing a torque, but he is providing a downward force. So the total force down is equal to the total force up. And when we start filling in some of these numbers, we have 30 times 9.8 for Jane, add 60 times 9.8 for the seesaw, add 72 times 9.8 for Jane's dad, and that is equal to the 1176 newtons of the support force upwards we just worked out at the force, the upward support force provided by the ground. So again, now that we've crunched those numbers out, you'll notice we've only got one unknown. So if we divide that sum on the left by 1,000, sorry, if we subtract that sum on the left, so if we subtract 1,176 newtons from that sum on the left, we will end up with the force of the support force of the ground. So 294 plus 588 plus 706 is equal to 1176 plus the support force of the ground, which gives us 1588 equals 1176 plus F ground. And finally, the support force offered by the ground vertically upwards is 1,588 minus 1,176, which gives a total support force of 412 newtons. So that question looked fairly straightforward to most people, and then when they started doing it, they just couldn't get their head around it. Part of the reason for that was that they were so focused on torques and looking at torques, they also forgot that in a situation involving equilibrium, the upward forces equal the downward forces. So while you have to start off working out the torques so that you can identify the support force, what you've then got to appreciate and realize is that the weight of Jane's dad, and the seesaw is taken or supported or shared by both the pivot and that point under the seesaw there where it's touching. So that force, and that force equals that one and that one. So once we worked out the force provided by the pivot point there in the first series of equations, then we had to work out what that downward force, and that downward force equal. Take away the bit that's provided by that pivot, and then whatever's left, the 412 newtons, that is what is provided by the ground there. That's probably the worst question I've come up against. By and large, you'll find ones very similar to the ones I did above. Usually the worst sort of one we get is one of those plate ones because students choose the wrong pivot. Hope these have been helpful to you. Take care. See you again soon.